Okay, so we talked about nucleation and growth during last week's lecture. And based on some of the questions that people asked after class, I didn't do a very good job explaining the topic. So I'm going to try explaining it in a slightly different way. So we're going to talk about nucleation and growth, or a phase transformation again. But I'm going to try to explain it differently to maybe help you understand it better. Okay? So in order to have a new phase, so phase transformation has two steps: nucleation and growth of the new phase. And so if we look at phase, we have a phase X, and it looks something like this. Okay, we have a phase, and under certain conditions, let's say a different temperature, different pressure, we can get phase Y. It's the same material, but it exists in a different phase. And let's say phase Y looks like this. Okay, so phase X, phase Y, same material, different phases. And if phase X is going to become phase Y, there must be a driving force. If it's going to change, there must be some driving force for that to happen, right? Materials don't just change for no reason. So we know the driving force is a change in the volumetric free energy. So the volumetric free energy, so GV, is volumetric free energy. So if we were to have this phase change, that must mean that the volumetric free energy of X is bigger than that of Y. So there's no reason to change if it's not going to get to a lower free energy. So any phase has some free energy associated with it. And for phase X, it is GV of X. For phase Y, it is GV of Y. So now we have phase X. It's starting to change into phase Y. So we have something like this. This is X. And we get a nucleus of Y. So here's our Y. And then here's our X. So phase transformation or nucleation started, right? Part of phase X has started to transform into phase Y. So there's a delta change, or there's a change in free energy. The change in free energy is a reduction of free energy because part of this material has started to change into a new phase that has a lower energy. So the energy reduction is 4/3 pi r cubed. So assume this nucleus has some radius r. So the energy reduction due to the formation of this new phase is G sub V Y minus G sub V X. So you end up with Y, you started with X. So that's the delta G sub V. And delta G sub V is going to be a negative number because delta G sub V Y, it's smaller than G sub V X. Okay, so this is the energy reduction when you have phase transformation. But you also have now a surface, a boundary between phase X and phase Y. And so energy increase is related to the surface area of the sphere and the surface energy. So if you were to look at the competition of these two energies, by forming a new phase, you get some energy reduction, but you also get some energy increase, right? So the overall change in free energy is a combination of these two. So if you were to plot delta G versus R, you get something like that. Okay, this is R star, and then I'm going to say that everything under R star is phase 1. Everything above phase R star is phase 2 or area 2. So under area 1, you have small nuclei that form. So if you get in phase 1, nuclei that form that are less than the critical radius, the nuclei will form. The reason why nuclei form is because of usually thermal energy, right? Atoms are moving around, they happen to get together, bump into each other, form a new phase. Because that new phase, when they bump into each other, the lowest energy state for them to be in is that new phase. But if they're too small, then it's lower energy state overall for that small nucleus to dissolve back into the solution, because it shows here, right? Energy lowers as you go smaller and smaller and smaller until you have no more nucleus. Phase 2, the nuclei will grow, because anything bigger than the critical radius, you actually get a reduction in free energy if you get bigger nuclei, if the new phase grows, right? So you could tell what will happen to the phase transformation by looking at the energy versus radius diagram. The system always wants to go to the lowest free energy possible. So with radii smaller than r star, the nuclei will shrink and dissolve away. With nuclei bigger than r star, the nucleus will grow and transform into a new phase. And then we went through some calculations last time to show that r star is equal to -2 times surface energy delta G sub V, and delta G star is equal to. So if you want to see how that was derived, you can review the video from last Friday. All right, so that's homogeneous nucleation. All right, any questions so far? I hope that's a little more clear than last week, but please feel free to ask. So what happens when you have heterogeneous nucleation? So in heterogeneous nucleation, your delta G sub V is still the same. So the change in volumetric free energy due to the phase transformation stays the same, because you still have a new phase that has a lower volumetric free energy compared to the old phase. And you're still talking about the same material, so that this part doesn't change. Delta G sub V is same as in homogeneous nucleation. But what is different is the surface energy. Because in heterogeneous nucleation, remember, you're adding other things to interact, catalysts, to interact with the nucleation process. So you're no longer just having this surface energy as a parameter in your considerations. Now you have surfaces, you have impurities, and there's interaction between all the different phases and all of the different boundaries, right? So what will happen is your activation energy is no longer just due to the surface energy between phase Y and phase X. Now you have all these other considerations that you take into account. And usually what will happen is that these other things will lower the activation energy. Catalysts lower the activation energy. So this equation no longer applies right here, because you have all these other surface energy that are in play. Okay, and that it will change depending on what kind of catalysts you have. So there's no set standard equation for the activation energy in heterogeneous nucleation. Depends on what kind of catalysts you have. But it will be lower than what happens in homogeneous nucleation. So if the critical radius of the nucleus is really small, let's say a couple of nanometers, that means that nucleation will happen very easily, because each atom in general is 1/10 of a nanometer. So if you have a couple of nanometers, that means 10, 20 atoms need to kind of happen to bump into each other, and they will start to grow, right? So if R star is small, then it's very easy for nucleation to happen. But if R star is big, then it takes more energy or more time or more catalysts in order for those nuclei to form. And so if we look at nucleation rate as a function of temperature, and we look at nucleation rate as a function of temperature because temperature is the energy that is around to overcome the activation energy. Atoms need to be able to move around in order to come together and form a nucleus that's big enough to grow. So the activation energy you could get from usually temperature. And that's why the rate of nucleation looks something like this. This is just temperature. So at the melting temperature, if you lower the temperature, at first, the temperature is too high, the nucleus might come together, the atoms might come together to form a small nucleus, but because there's so much energy, they come apart again. So it's very slow to form any kind of nucleus because they're still moving around too fast. You cool it down some more. Now it's more and more likely for the nucleus to form of the critical size. And then at some point in optimum, and then as you lower the temperature some more, now you have too little thermal energy for the atoms to come together. So at some range, you say that this is optimal transformation. This is just an estimate. It's just, if the energy is too close to melting, too much energy around, it's difficult for the nucleus to form. If the temperature is too low, not enough energy to overcome the activation energy, so you also don't form a nucleus. But somewhere in between those two, you will get the most amount of phase transformation. So that's nucleation, and then growth. So growth happens once you have nuclei that's bigger than R star, right? Because if you have nuclei that's smaller than R star, they'll dissolve away. They won't grow. But if you have a nuclei that's bigger, so if R is greater than R star, then you'll start to have growth. And the growth rate is a function of temperature, and it looks something like this. Obviously, once you get past higher than the melting temperature, you're not going to get growth of the solid phase because there's no longer a driving force for the solid phase to form, right? The volumetric free energy no longer favors the solid phase. So you get no growth above the melting temperature, if we're talking about liquid and solid as the phases. Okay. But under the melting temperature, now of course, the higher the temperature, the better, the faster the growth, because growth is based on temperature, is based on diffusion. And we already saw that the rate of diffusion is relative to the exponential of negative Q over KT, the Arrhenius equation, right? We had talked about diffusion earlier in this class. We know that diffusion is related to temperature through an exponential equation. So the growth rate would look something like this, exponential curve. So really high growth rate at temperatures close to the melting temperature, and then low growth rate as you lower the temperature. Because in order for the new phase to grow, atoms need to move to the nucleus so the nucleus can get bigger and bigger. All right, so hopefully that's a little bit more clear than what we talked about last week. So now we will talk about something called TTT diagrams. So that stands for temperature, time, transformation. People use these kind of diagrams a lot for common alloys to figure out how much time you need at any given temperature to form different kinds of phases, right? So if we are trying to make a specific kind of iron alloy, we need to know what phases are present, which is what the phase diagram tells us. But we also know how much time we need. So remember, phase diagrams are for thermodynamically stable phases. They don't tell us anything about rate, how fast these phases form. So you need a different diagram that can tell us more about how quickly these phases form. Okay, so that's the TTT diagram. So let's look at the iron-carbon phase diagram there, and we have 0.76 weight percent carbon at 600 degrees Celsius. And I'm going to draw a TTT diagram here. This is temperature, this is time. This is my eutectoid temperature. So what is my eutectoid temperature? It's on the phase diagram. Yep, close to 720, right? It actually tells you here, 727. So eutectoid is when one solid phase under the same concentration, when you lower the temperature, becomes two new solid phases. So the eutectoid point is here, and the temperature is right here, and they tell you it's 727. And I want to know what happens at 600 degrees C. So the region above the eutectoid, what phase do we have? Above 727 degrees Celsius at 0.76 weight percent carbon, what phase do we have? Okay, so at T above 727 degrees C, and at this concentration, we have austenite. If we were to cool, so let's say we're somewhere at 800, and we were to cool it down really quickly to 600, very, very quickly, say within a second, what phase would you expect? So if we were to cool to 600 C quickly, and a lot of times that's called quenching. When you cool something very, very quickly, it's called quenching. So we quench the metal to 600 degrees C. What do you expect might happen to the phase? What phase might you have? Based on what you know about nucleation and growth, and also the phase diagram there, you'll still have austenite because you didn't give it enough time, right? Do you think that that phase is stable? No. Why is it not stable? How do you know that? How do you know that austenite at 600 degrees C and 0.76 weight percent carbon is not stable? Right, because you can see on the phase diagram what is the stable phase? Alpha or ferrite, right? So very good. So we know that if we're looking at this diagram, we know that above the eutectoid temperature and at this composition, we have here, this area would be austenite, right? Either high temperature or low temperature, but very, very small amount of time. You get austenite. If we were to leave it for a long, long, long time, okay, so we cool it to 600 and we hold that material at 600 for a long time. We start with austenite. What do you think might happen after a long time? What might you get? Perlite. And perlite is a combination of alpha and cementite, but they're layers. Okay, so that's what you might see here. At 600 degrees C, you hold it for a long time, and you get perlite. So the phase is here. And you also have perlite here. But there's some difference between the two perlites. What might you expect to be the difference between the perlite here and the perlite here? So if you're 600 degrees C, 0.76 weight percent carbon, you quench the material really fast, you get austenite. You wait, you hold it at 600 and you wait. Eventually it becomes perlite, and you wait longer, it stays perlite, but there's some change as time goes on. What do you think might change? Let's see, this is. Something like that, okay, that's perlite. Looks something like this. What might change as you wait? So all systems want to go to a lower energy state, right? You're giving it time to go to a lower energy state. How can this change to lower the overall energy state? How could this phase? You already have the most stable two phases. You already have alpha or ferrite and cementite. You already have those two phases, which are the thermodynamically stable phases. So you know that it's not going to change phase anymore because those are the two most stable phases. What's going to change to lower the overall free energy here? How can this, fewer grain boundaries, right? How can it have fewer grain boundaries? Thicker layers, right? So you can have so it's still perlite, but the layers can become thicker. So the TTT diagram, how long you have to wait for these different phases to happen, for these transformations to happen, is determined by experimentation. So people take a alloy of a certain concentration composition, and they heat it to different temperatures, cool it down to different temperatures, hold it at different amount of times, and then they look under the microscope to see what happens, right? And then they could, after testing for these different amount of times, they could draw these diagrams. And once they draw these diagrams, this really helps you in being able to figure out how long you need to hold your material at what temperature in order to get what kind of microstructure. So you want perlite at 0.76 weight % carbon. You want to know how quickly do you need to, you could either quench it and hold it, or you could cool it very, very slowly, right? You have different ways of getting there. So the TTT diagrams are really helpful for material scientists who are actually making these different materials to figure out, okay, how fast do I need to heat it? How fast do I need to cool it? How long do I need to hold it at what temperature? And once you get to, let's say you want perlite, and you want this kind of perlite, then you don't want the layers to get any thicker. What might be one reason that you don't want the layers to get thicker? Why might you want this instead of that? What kind of mechanical properties might be better under this structure compared to this structure? What is it?
Brittle.
Okay, brittle, or another way to say it would be harder, right? Okay, so this will have higher hardness and also more difficult to deform, so higher strength. This will be more ductile, right? Easier to bend, this one. The reason why this has higher hardness and higher strength is more grain boundaries inhibit slip or dislocation movement, right? Dislocations can't move through as easily, so it's harder and also higher strength. Okay. So you want a material that's hard, has higher strength, so you know that you don't want to keep going here. So what you might want to do here is once you hold it for a certain amount of time, you know how much time because you have a TTT diagram, then you quench it really fast from 600 so that you hold whatever form you have in place to room temperature, right? Okay. Any questions about TTT diagrams? Yeah.
How do you define the boundary between the two parameters?
How do you define the boundaries? It's based on experimentation. So if they see that there's some substantial change, they might call it a new boundary. So we don't actually have much of a change because we're at the eutectoid composition. But if we were at a hypoeutectoid, there may be more of a difference after a long time because you get both perlite and ferrite, and the ferrite might grow to become bigger, right? And not in a layer form. So you might get different structures, and that's a good question to lead into the next topic, which is what kind of different structures might you have? So we already know about one structure, and that's perlite, right? We know perlite is layers of ferrite and cementite. So we have perlite. So the things I'm going to talk about now are microstructures, what the materials will look like, not phases. These are phases. Ferrite, cementite, austenite, liquid, those are phases. Those are structures, FCC, BCC, those kinds of things, okay? Microstructure is what the material actually looks like under the microscope. So microstructure of perlite is made out of two phases, ferrite and cementite, and it's a layered form. So I have pictures. And we have perlite here. This is perlite, right? This is what it actually looks like under the microscope. Okay, so you'll see layers of one phase and another phase. And the phase is kind of squiggly, and that's why they call it perlite, kind of like a string of pearls almost. There's something else called bainite. Bainite is if the alloy is cooled. Okay, so bainite is also layers of alpha and Fe3C, or ferrite and cementite. But because it's cooled to below the optimal phase transition temperature very quickly, the individual layers don't have time to grow. They have to form very, very fast. And there's not much time for diffusion. And so the layers are very, very fine. So really, really tiny layers. And so it's actually usually not able to be seen under the microscope. So you actually might not see the layers because they're so small. So how would you know? Okay, well, let me get back to that. So that's bainite. So very, very fine layers. You almost can't see them unless you use a very high-powered microscope like a SEM, scanning electron microscope. There's another kind of phase, and these are spheres of Fe3C in an alpha matrix. So we actually don't have any spheroidite in this picture, but you get alpha. Most of the places is alpha, and then you get little spheres of cementite. So what do you think might be required to form this? In terms of time and temperature, do you think it takes a long time or a short amount of time to form spheres of Fe3C within an alpha matrix? So we know if it's layers, it's perlite and bainite. If it's spheres, then it's spheroidite. So which one do you think will take longer to form, layers or spheres? Spheres, right? Because there's more diffusion that needs to happen in order to form a sphere compared to layers. So it'll take a long time. And it needs energy for diffusion. So probably at an elevated temperature. You need to hold it at an elevated temperature for a long time. So let's say you have a material that doesn't look like it has layers. How might you be able to tell if it's a bainite or some other form? Let's say we have something like this. That it's perlite, a little bit of perlite and a lot of ferrite. So you don't see a lot of tiny layers, right? How would you know if it's a bainite? So you're looking under the microscope. You won't be able to tell by eye, so you can't tell by looking at it if it's something like that or if it's bainite. So what can you do, you think, to see if it's a bainite or something more like that? What is an experiment you could run? Mechanical property-wise, what do you think will be different between bainite and that over there? This has lots and lots and lots of fine layers, lots and lots of grain boundaries, right? So this will be hard and brittle. And that one will not be nearly as hard or brittle, right? So if you just test it for the hardness, you can tell if you have bainite or you have something that doesn't have any layers. And then tomorrow I'll finish up on phase transformations, and then we'll move on to chapter 11.